I'm not going to talk about the chemistry of catalysts, but I will talk about the kind of a special technique to enhance the adhesion of catalyst onto kind of like metallic substrate. There are some applications of the catalyst using the metal substrate, so probably this might be for some special applications for the user's gas application. First, I'm going to talk about why we start this one. So why we were interested in this one. And then I'm going to show some interesting results using this special coating technique called like powder spray coating for aerosol deposition. And then, I'm going to wrap up the results after that. Probably this is not for the automobile applications. I'm more interested in actually marine applications. 6 or 7, maybe 7 or 8 years ago, after I came back from the United States, I didn't have much for the research for the automobile uses actually. So, but at the time, I had a chance to do some projects relating to ships. It's kind of like an internal project. And at the time, I was interested. We had been interested in the new regulation for marine ships. Probably some of you saw these kind of pictures. So new regulation called IMO Tier 3 started from January 1st of 2016. So we need to consider, we need to develop new technologies to reduce the emission of NOx from ships. These maps shows the NOx emission distribution. It is almost similar to the paths of ships, big ships. This is a typical picture of two-stroke engine for propulsion of ships. And there are a lot of the emissions from ships, of NOx from ships. I think Dr. Song is more the expert in this kind of engine. So a lot of NOx comes from the marine engines. And we need to decrease the huge amount of NOx emission. And then it depends on the RPM of ships. And in the beginning, we are interested in the low RPM, means like big engines. And as you know, the SCR technology is the kind of more efficient technology for the NOx reduction. So it's kind of we know that it's kind of like old technology, and this kind of simple reaction using the SCR. And actually, we are focused on two types of typical catalysts for the NOx. One is vanadium, the other one is zeolites. You know the zeolites cannot be used for the marine application, as you know, because of the loud sulfur. But we tried both materials to enhance the adhesion, depending on the application. There are two types of typical monolysis catalysts. One is extruded full body catalyst, which can be used for like a plant or stationary applications. The other one is coated monolysis. So we are not interested in this one. So we try to develop the new coating technology for this kind of coated monolysis. there was essential technology for stationary applications. But we are wondering, can we use this technology or can we apply this technology to marine application directly or not? Because the environment or conditions are very different. This is mobile, this is not mobile. And this has just very small space to install the essential system. So we need to think about some other things. So for the marine applications, we need to check or we have to consider these kind of many parameters to develop new types of catalysts. And like a space velocity, temperature, sulfur, vibration, pressure, there are so many things to be considered. And at the time, there are two types of the essential system called HP and LP. HP is kind of a pre-turbine essential, and LP is kind of after-turbine essential. There is a big turbine in the marine engine system. So maybe Doosan engine is focused on this kind of after-turbine. So turbine, engine, turbine, and then catalyst system. And Hyundai heavy industry has been developing the two types, both LP and HP engines. But pre-turbine SCR this one is very close to the engine, just next to the engine room. So there might be big vibration or some like a chemical effect. So we need to, if we want like coated monolis, then we need to develop like a more durable, mechanically durable catalyst. So that's the reason why we are interested in the enhancement of coating the catalyst cause adhesion. This picture is kind of old one. H plus H is a German company developed the SCR system for marine. This was sold out to big company now. But at the time they were developing SCR system for a four-stroke engine having two turbines. So they need to install this SCR system on top of the engine. That means there might be a lot of vibration. So they apply the metallic substrate to develop the SCR system for this engine. But I didn't hear about the test results. For coated monolith catalyst, we have two typical substrate, honeycomb substrate, ceramic. So for automobiles, mostly like ceramic monolith has been used. But for expensive cars like BMW, Benz, they start to use metal monolith recently. Metallic monolith has many advantages compared to the ceramic monolith, but it's a little expensive because it uses expensive stainless steel materials, and the catalyst is mostly like a ceramic-based materials. So we have the adhesion between the substrate and the ceramic-based catalyst is normally not good. So if you want the metal monolith, we need to consider how to enhance the adhesion between the monolith and catalyst. This is a typical wash coating or impregnation technology to be for like automobile or other catalyst applications. And this is conventional like monolith catalyst, the coated monolith having the nano-sized catalyst inside. And this is typical TWC catalyst. So now I'm going to talk about some kind of like a special, unusual technique for coating. It can be called like a powder spray coating. We didn't use wet solution. We use a solid powder, and we directly coat on substrate. And this one was a typical SEM picture of the coated catalyst. I will show later, more later. This is kind of like a mechanism of coating. There's a vacuum, gas. So there's carrier gas. The gas carries the powders, and it shoots the powder on top of the substrate. Seeing is believing one more time. Actually, we don't know the exact mechanism why it's make a huge adhesion, very strong adhesion in detail. But we guess some. You can make a new surface, non-contaminated surface during coating. So we guess the new surface can make like a very strong adhesion. And there are some advantages. You can make like a very thick layer, like 100 micrometer, with very fast. And we can make a thin and thick coating without cracks. And we can coat it or dense or porous the substrate. We can control the stoichiometry because we didn't change the powder. We don't have to change the powder. We can use the raw material of powder. So that means we don't have to worry about the stoichiometry and completion of the coat. This is a typical microstructure showing the porosity of the coats. We can make it dense. We can make a very porous layers using this technology. First, we tried ion GSM1, GSM5 catalyst, typical catalyst for the NOx. And this one is low powder of ion GSM5 to the catalyst. This is slurry, the ion GSM5 coated by slurry wash coating, conventional wash coating. And this one is excited pattern of the ion GSM5 by this technology. It shows the base was not changed. And the bandwidth a little broader. That means the crystal size might be smaller, got smaller. On the left side, we wash coating using in-house machine. We made the wash coating machine in-house in our institute. So using the machine, we wash coating, and this is SEM picture of the wash coated layer. And this is a little thin layer, 5 micrometer. This is the coated layer using our technology. The microstructure, this one looks very porous. Both look similar. We didn't expect the increase of performance using this technology. We expected same performance with very strong adhesion. And we wanted similar microstructure using this technology. This one are medium thickness, like a 220 micrometer. Looks similar. So conventional coating and special coating. We did 50 micrometer using this technology. So, in regardless of the thickness, we made a similar microstructure using this technology. And then we tested adhesion using the conventional ultrasonic test. We put the samples in the ultrasonic cleaner and vibrate it, and we checked the rate of the loss after drying the sample. This one, the slurry coating without binder. I used the typical binder from Germany, like a starting S. This is without binder, the blue one, and this one is with binder, 3%, and this one with binder, 6%. So these three were made by like a conventional slurry wash coating using the wash coating machines. And this is our coating, the special coating. This is like a thin, the low loading samples. Means a thin wash coat. 1 minute, 2 minutes, 3 minutes, 5 minutes. After 5 minutes, this one, most of calories gone. With more binder, less loss, but still a lot of the calories were gone. But our sample, no loss for the low loading. 20 grams per liter, the corresponding calories loading of 20. Similar one, but slight loss of our calories. Corresponding calories loading 50 grams per liter. The amount of loss of calories a little increased, but still very low relative to the conventional wash coat. So most of the wash coat was done after the heavy test of using the ultrasonic tester. Corresponding calories loading 170. It's typical loading for the automobiles, especially PWC. And we still had a very good adhesion. So our coated samples have excellent mechanical durability, even with very high calories loading, showing very strong adhesion strength to the substrate. And then we tested the NOx performance using the sample. So people can think, oh, okay, this might be dense, so there might be no activities, catalyzed activities, because it's dense, to get adhesion, strong adhesion. So we tested the NOx test. We made samples, 4 samples, 1 inch, the typical ones the catalyst company is using. And we spent a lot of money to build this one. So left ventilator, like this. And we have another consecutive caloric method for monolysis, catalyst. Maybe it can be used like a DOC, CPPF, SCCF consecutively. We spent a lot of money again. So we tested the core samples. Actually, at the time, I was so surprised. I didn't expect any NOx performance. Very low loading, with very low loading, there was NOx performance, even though it's very low. Because the loading is very low. So I was so surprised. Oh, there might be something. So this is, we tested 2 space velocities. And we increase space velocity, lower NOx conversion. I think it was, the catalyst was I didn't make this catalyst. I was provided by the company, but it's not the formulation of. I think the formulation was not perfect at the time. We increased the level of loading to 75 gram per liter. And this one, our sample, the new sample. This one, the wash coating sample. So we didn't add any NO2. We just used the NO. The performance itself is not good, so you don't consider this absolute conversion. Just we need to compare between two samples. So we got very similar the NOx performance. And we increased the space velocity, so it's very similar to the conventional catalyst. And we changed the concentration of NOx, NO 250 to 500. And we added some NO2 to check the effect of NO2. So we got a very, very good performance, even though we not optimized the samples catalyst. So every samples we can obtain the similar performance. So that was our goal. And then actually the previous these samples, I don't think that we can commercialize this technology to apply to real system. So we did another one. We just pre-coat using the technology very fast, and kind of like a pre-coat of TiO2 to coat the vanadium-based essential catalyst. We made the sample. This one we coat conventional titanium powders used for the essential catalyst. So this is the low powder, mixed with the rutile and anatase, the TiO2. This is coated TiO2 on the stainless steel 444 substrate. It's cheap one, much cheaper than the petroleum. And this is intermediate layer of TiO2. The SEM pictures, you can see the very good adhesion between the TiO2 intermediate layer and the substrate. So we made 3 samples. One is cordialite substrate. The other one is without pre-coating, with pre-coating. And after adhesion test, with the samples without the TI coating, most of the wash coat was gone. So we wash coated after the pre-coating of TiO2. And then we did the adhesion test using the sonic cleaner. And we checked every minute to check the loss of the coat. And these red ones are samples without pre-coat. And depending on the level of the wash coating. The blue ones is the pre-coated samples. And we wash coated TiO2 powder only. And we call it vanadium-based the catalyst coat. So we got the similar trend to show the strong adhesion enhancement by the pre-coat. And we tested that NO conversion. And this one, cordialite, this is the before adhesion test, these 3. And these 3 are after the adhesion test. The cordialite samples was the best, showed the best NOx performance. And the stainless steel substrate sample is a little lower, the NOx performance. But after adhesion test, the samples with the intermediate layer showed that the highest the NOx performance. So our institute developed a new coating technology, and we tried many applications, including the catalyst, even including the photocatalyst. So I think we need to commercialize this technique using some engineering developments. So I think it's good time to collaborate with the people in our field. Thank you.